Scientists have discovered a new window into the Earth's violent past. Volcanic rocks collected on Baffin Island in the Canadian Arctic suggest that beneath it is a region of the Earth's mantle that has largely escaped the billions of years of melting and geological churning that has affected the rest of the planet. Researchers believe the discovery offers clues to the early chemical evolution of the Earth. The newly identified mantle reservoir dates from just a few tens of millions of years after the Earth first formed from collisions of smaller bodies. This reservoir likely represents the composition of the mantle shortly after formation of the core, but before 4.5 billion years of crust formation and recycling modified the composition of most of the rest of Earth's interior. This time was a key phase in the evolution of the Earth. The research is described by Carnegie Institution scientist Richard Carlson, lead author and former Carnegie postdoctoral fellow Matthew Johnson, now at Boston University, and co-author Don Francis of McGill University. The scientists targeted Baffin Island because rocks there have anomalously high ratios of helium-3 to helium-4. Helium-3 is generally rare within the Earth. Most of it has been expelled by volcanoes and lost to space over geological history. In contrast, helium-4 has been constantly replenished within the Earth by the decay of radioactive uranium and thorium. The high proportion of helium-3 suggests that the Baffin Island lavas came from a reservoir that never got rid of its original helium-3 because it had not been subjected to the extensive chemical changes in most of the mantle. Lead isotopes and lava samples confirm the age of the reservoir at between 4.55 and 4.45 billion years old, an age only slightly younger than the Earth itself. The early age suggests that the reservoir existed before the formation of the Earth's crust and before plate tectonics mixed the crust back into the mantle. Many scientists believe that the Earth's early mantle was similar to meteorites called chondrites, but that the formation of continents caused it to become depleted of so-called incompatible elements. This new research suggests that the Earth's mantle was depleted of incompatible elements even before continental extraction. This suggests either an earlier differentiation event or that the Earth was initially formed from building blocks that lacked these elements. The early differentiation model involves a global magma ocean that produced a crust before the crust that exists today. Because it was rich in iron, the crust was buoyantly unstable and sank, taking the incompatible elements with it. The research appears in the August 12th edition of Nature. This is John Strom for the Carnegie Institution. There are places in space where the gravitational tug between a planet and the Sun balance out, allowing other, smaller bodies to remain stable. These places are called Lagrangian points. So-called Trojan asteroids have been found in some of these stable spots near Neptune. Trojans share their planet's orbit and help astronomers understand how the planets formed and how the solar system evolved. Now, Scott Shepard at the Carnegie Institution's Department of Terrestrial Magnetism and Chad Trujillo of the Gemini Observatory in Hawaii have discovered the first Trojan asteroid in a stability region at Neptune called the Lagrangian L5 point. L5 has been very difficult to observe in the last several years because the line of sight of the region is near the bright center of our galaxy. The scientists devised a unique observing strategy. Using images from the digitized all-sky survey, they identified places in the stability regions where dust clouds in our galaxy blocked out the background starlight from the galaxy's plane. This provided an observational window to the foreground asteroids. The discovery was made using the 8.2-meter Japanese Subaru telescope in Hawaii and Carnegie's 6.5-meter Magellan telescopes at Las Campanas, Chile. The L5 Trojan has an orbit that is very tilted to the plane of the solar system, just like several in L4. This suggests they were captured into these stable regions during the very early solar system, when Neptune was moving on a much different orbit than it is now. Capture was either slow, through a smooth planetary migration process, or as the giant planets settled into their orbits, their gravity caught and froze them into these spots. The work was funded in part by the New Horizons spacecraft mission to Pluto, which will pass through this surveyed region of space on its way to Pluto in 2015. The research is published in the August 12, 2010 online issue of Science Express. This is John Strom for the Carnegie Institution. Superconductors can carry electricity without resistance, so they're more efficient than normal copper wires. However, these materials have to be cooled to a very low temperature, known as a transition temperature, before electrical resistance disappears. Developing superconductors with higher transition temperatures is one of physics' greatest quests. Recently, scientists found that subjecting certain materials to extreme pressure can produce higher transition temperatures. Now, researchers at the Carnegie Institution's Geophysical Laboratory, with colleagues, have unexpectedly found that the transition temperature in a three-layered bismuth oxide crystal, referred to as Bi 2223, exhibits rising transition temperatures at two different pressures. They believe this unusual two-step phenomenon comes from competition of electronic behavior in different kinds of copper-oxygen layers in the crystal. Bi 2223 is like a layered cake. On the top and bottom are insulating bismuth oxide layers. On the inside of those come layers of strontium oxide. Next are layers of copper oxide, then calcium, and finally the middle is another copper oxide layer. Interestingly, the outermost and inner layers of copper oxide have different physical properties, resulting in an imbalance of electric charge between the layers. The scientists doped the material with charged particles, which also helps raise the transition temperature, and then subjected it to pressures up to 359,000 times air pressure at sea level, the highest pressure obtained for this material. They found that the transition temperature went up at pressures beginning at 100,666 atmospheres. But after that, more pressure ended up with lower transition temperatures. The reduction of the transition temperature stopped at 237,000 atmospheres, and at 359,000 atmospheres, the transition temperature rose again. The researchers think that 237,000 atmospheres might be a critical point where pressure suppresses one behavior and enhances superconductivity in layers that exhibit different properties. The findings may offer a promising way of designing and engineering superconductors with much higher transition temperatures. The research was supported by the U.S. Department of Energy, Carnegie, Canada, and the National Natural Science Foundation of China. It's published in the August 19, 2010 issue of Nature. This is John Strom for the Carnegie Institution.